Hello. Thank you for uh, coming to my talk. I'll start. So if you're a software developer like me, you probably spend a bit of your workday looking at things on Hacker News, and often you would think that Rust and probably Go are like the only programming languages because you see a lot of activity and talk about these new languages. And sometimes it's kind of hard to separate the hype from the real benefit that you get from this. So my talk today is simply to give a very unbiased view about Rust. So try to essentially answer uh, five or so questions about it. So one, I will talk about the question of when, this being in regard to time. So how did Rust start? How has it evolved over time? And how has the development been like? Who are the key people in the project? Two is the why question. Why is Rust actually existing? What was the reason of having a new language? You already have, I don't know, probably over 100 languages there, and it's you could argue that we already have a language to solve the problem you have, and so I would try and highlight some key problems that we have, more so relating to systems programming and how Rust tries to solve them. Then I'll move on to describe the what and how of Rust, so in terms of the semantics, the code, and how the problems that Rust aims to solve have been solved in the language. And then at the end of my talk, I will talk a bit about people who are using Rust, companies in production, and also the community. So how I got into Rust was mainly through the community. So it's a really nice, welcoming community. And this wouldn't be a Rust talk without at least saying a few words about the community. Okay. So before we dive in, I would like to just introduce myself so you kind of get an idea um, who I am. So my name is Matt. I work at a company called Snips. It's a French company, and we build voice recognition algorithms so for IoT devices, so embedded environments. And we happen to use Rust, so our code on device is all written in Rust. I also happen to do a bit of community work in the Rust community. I'm a member of the community events team, so I volunteer a bit of my time in growing the Rust community. I also was an organizer. I still also am involved a bit in the Rust Nairobi Meetup. So before I moved to France, I started a Meetup group in Nairobi to talk about Rust, give talks and workshop, talk to new graduates and introduce them to the language. Yeah. So yesterday I heard people are not willing to ask questions, so I would encourage you. There is at the bottom of my slides, some of my slides will have my Twitter handle. If you have a question during this session, feel free to tweet at me, and at the end of the session, I'll try and look at some tweets and answer the questions. Okay. Cool. So we're going to begin with when, right? The Rust as an idea has been there for quite a while. So it started as a personal project. You have this engineer who was working at Mozilla who was trying to build something that would kind of fix some of his frustrations that he had seen in writing C and C++. And so his name is Graydon. Here is someone asking him how long the name has been, and he kind of mentions more or less 204, 205. And he did a presentation in 2010, and by this time he had already built sort of like the initial version of the language. And so this was more or less the early on goals that the language had. So concurrency, safety, and it's supposed to fit in the same niche as C and C++, so systems programming. And one of the key things that were also there at this time in the language is that there was a type system. It had mutability control. So Rust is by default immutable. So when you declare a variable, by default they're immutable, and you have to use a keyword to actually, for you to be able to mutate them. Also, it had a side effect control. So it began sort of from a functional programming route. So when I say side effect, I mean it was a pure, it had pure functions. Right now it's changed, so that's not the case. And around this time also, the compiler itself was written in OCaml, which is a functional programming language. Yeah. So this is a snippet of some of the code from back then. If you're familiar with Rust, you can see that a bit of it has changed, but it gets, you can see some of the things that have been carried on, such as the FN keyword, and also how we do the if-else. So I have this simple graph that tries to talk about Rust over time and show some interesting dates and timelines. So I mentioned the project started as a personal project by Graydon in around 2006. And then in 2009, Mozilla started sponsoring the project. So there was like a small team at Mozilla full-time working on the language. And between 2009 and 2015, a lot of things changed. So 2015 is important. May of 2015 is when Rust released the 1.0 release. So this was a stable release guaranteeing backward compatibility in the language. So here, one of the things that changed is the compiler got rewritten from OCaml to actually using Rust. A lot of there were improvements in the type system, the ownership model, if you're familiar. I'm going to talk about it later. Essentially how Rust deals with memory came during this time. Also, there's the RFC process. So all the features that come into the language are sort of done in sort of consensus. So you have to write an RFC, and that goes through some stages where people discuss and try to get the merit of it. And once the RFC is approved, then the feature can be implemented. So this came up during this period. Yeah. And then, so the line in blue is just a trend on Google, just showing how much people have been interested in Rust over time. And the green line is showing the growth of developers, contributors who have contributed to the Rust compiler. So it's important to note that Rust development has been open. So it's you can go on GitHub and actually find the whole history. And a lot of the people contributing to the compiler are not actually people employed by Mozilla. These are folks on GitHub seeing an issue and doing a PR. And so that's how the graph has grown. Right now, it's we almost have, I think, when I checked, it was almost 2,700, almost 700 contributors who have contributed something to the compiler. And so right now, this is sort of what you have current day snippet of Rust code. I have marked part of the code with these cute crabs, so essentially to highlight some of the features. So like at the top, you can see there's this a hash and then there's a derive and there's this debug thing. And this is a macro. So we have two types of macros in Rust. So there's one at the top and one at the bottom here with the println. So these essentially help you to do a bit of meta programming. And if you're familiar with Haskell, Haskell has something similar where you can do like a derived show for a certain struct. And the idea here is that in this case, this debug macro will provide us a way of printing out this struct. So, and when you print it out, you call it with this interesting syntax here. So you essentially saying that the thing that comes here should be formatted using this debug mode. And then you just pass in our rectangle here. And then so we have a struct, pretty similar to what you have in C and C++. And then there is an implementation block. So this is where we define behavior to our objects. So you have an associated function. So this is a constructor. The new word is not a keyword. It's just a convention that we use when building an instance of a struct. And you can see it's an associated function since we don't have a self. And this is an associated function. And it kind of almost looks like what you'd have in an OOP language. Yeah. Okay. So that was a bit of the history of Rust, how it has moved from being a personal project to an open source project, and the features and how it's changed in terms of syntax and all that. But you might have the question of why does Rust actually exist, and what is it trying to solve? So Rust is primarily designed to solve two problems. So during this period between, more or less from 2009 when it was adopted by Mozilla, they were doing a lot of experimentation on their browser. So they have a browser engine written in C++ Gecko, and Mozilla Research had another experimental engine called Servo, and this engine was written in Rust, and they would develop the engine and do sort of feedback that influenced in how the Rust was developed, and features or like show pain points that they had. So the two main things that Rust tries to solve, one is concurrency. So it's simply how can we make concurrency less painful. So if you think of concurrency, it's simply where you have multiple things running at the same time. And it's actually good for performance because, one, we get to exploit the resources we have on our machines. So over time, Moore's law has more or less slowed because physically we can't fit as many transistors on a silicon chip anymore. And now, ideally, how you scale up is you have a chip with multiple cores on it. And here, concurrency comes into play because if you're able to run your program on all the cores available to you, then it means you'll have better performance. But then this sort of programming comes with a bit of complexity. So one of the issues you have is a race condition. So if you, the classic example, if you have two threads that are updating a value, so they read at the same time, let's say this value is 1, and they want to increment it by 1. They read at the same time, each one has the value 1, they increment it to 2, and then write back, and you kind of have one of the writes being lost. Another issue with concurrency is deadlocks. So you have two threads that are waiting on each other to release the resources, because both of them need the resources from each other. And so you have this situation where you're doing nothing because you're more or less halting, waiting indefinitely for the other thread, and the same thing because the other thread is waiting for you. And another big issue with concurrency is that, and I think this is what this comic tries to illustrate, is sometimes you can have bugs that occur since you, by virtue of doing concurrency, there is no inherent guarantee in the order in which your code is executed. So if you get a bug, then it's very hard for you to actually reproduce it, or even actually debug it. So Rust ideally tries to get rid of these problems that come with concurrency. Then the second thing is about this. So who in the room remembers this logo? All right, yeah. So this happened a few years back, where there was a bug in OpenSSL. Essentially, there was no bound checking on an array, and you could essentially read beyond the array in memory and get very interesting things such as people's password and messages from web servers. And this affected a lot of web servers on the internet. And the issue that we have this kind of bugs is because the languages that we use to write web servers, so these low-level languages, C and C++, are inherently unsafe. So they don't stop you. As a good programmer, yes, you should know you should not read beyond the end of an array. But they themselves, the language, if you do that, they don't stop you. They assume you know what you're doing. And it leads to problems like this. But it's also important to note that, yes, there are some languages that have fixed these issues. So if you are using a higher level language, Java, Python, Go, they make sure that you can't do something like this. If you have a container, you cannot access the index past at the end of the container. But then the issue with these higher languages is that for this safety that you get a performance penalty. So if you're using Ruby or Python, you have a runtime. So essentially a garbage collected runtime that will influence essentially how performant your code is. So it's not going to be as fast if you had written it in C or C++. And also, it takes away the control you have when you're writing C and C++, because you yourself can decide when to allocate and deallocate memory. But if you're working on a higher language, all that is done by the garbage collector, and you have no way of actually influencing that. Yeah. So the idea here is that Rust will try to fix a few issues, so it will handle buffer overflow, avoid you having dangling pointers or like using memory after it has been freed. And I think this quote kind of exemplifies that we should actually be careful in the languages we use, because such a bug, if imagine for whatever reason in the future you have this bug that affects all the computers in the world, then we would have a serious issue on our hand. And making sure that we actually build sort of strong foundations for our computation is actually something good. So this is a quote from Tony Hoare. If you are not familiar with him, he's a British computer scientist. If you know Quicksort, he came up with Quicksort. He also did a bit of work in creating logic for verifying program correctness. So there's the Hoare logic. And he done a bit of some work in distributed computing. So essentially, he came up with a CSP, communicating sequential processes. All right. So now let's look at what Rust actually is. We know why it exists. So for the longest time, if you went to the Rust website, this is the description you get. It's a systems language. It runs fast. It prevents seg faults, and it guarantees some sort of thread safety. But if you're someone like me, because I come from a Python world, or if you do JavaScript and you read this, you'll be like, what? Blazing fast, yes, I understand it's good to be fast, but we don't talk about seg faults in JavaScript or in the Python world. We rarely talk about memory safety. So there was this a bit of discontinuity in terms of like introducing Rust to people who are not actually systems programmers. So eventually, the description has evolved over time. And I actually like this quote from Ashley Williams. She's a member of the Rust core team, and she also does a bit of community work. And essentially, the idea is that Rust is simply supposed to empower you as a developer to write code that is fast and also safe. And I will touch on what we mean by actually saying empowering. So talk about the productivity that Rust gives you as a developer. Yeah. And I think, to me, that is more or less a good introduction or description to Rust. So another way I personally like to look at Rust is based on the three main goals that it tries to solve as a systems programming language. So someone told me every talk must have a Venn diagram, so here is mine. So the three things, we've kind of touched on two of them, so concurrency and safety. And there's speed, so essentially Rust is supposed to be comparably fast as C and C++, because the idea was to use it as either together with them or a replacement. So speed is one of the key things that Rust aims to do. And then we've touched about the safety aspect, so being memory safe and making sure we can't have these bugs that are very easy to do in C and C++. And the other big thing is that we should support a way to do concurrency and make it really easy for a programmer to do that. And I think Rust sits in that, the intersection of these three main goals. So we're going to look at how Rust achieves the three things. So first, we're going to look at speed. So there are several things that Rust does to be fast. And if you go, there are a lot of benchmark that shows, comparing Rust and C or C++. And I'm not going to show any benchmarks here, but you can find a lot of them online. So one of the big reason for Rust being fast is that it doesn't have a runtime. So there's no global penalty that you get like when you have garbage collection in a garbage collector language, because the way Rust manages memory is all done at compile time. So there is no runtime when your code is running, and this makes it fast. And also another thing that comes from this is that Rust can run sort of anywhere C can run. Because you don't have a runtime, then you can use Rust, for example, in embedded environments where you're kind of constrained in the resources that you have. Another thing is the Llvm. So Llvm is a collection of compiler tools and techniques that help you to build compiler backends and frontends. And it's been there. I think it came out of The LLVM doesn't mean anything, but some people say low-level virtual machine, but it doesn't have quite a name. But so the Rust compiler is simply a front end to Llvm. So part of, and I'll show a slide that kind of explains this. When your Rust code gets compiled, it will be compiled to an intermediate representation that is then passed to Llvm, and then Llvm will do other optimizations and emit the machine code. And then two other things. So we have these two last points, zero-cost abstractions and generics. And these are kind of closely related. So with zero-cost abstractions, the idea is that Rust as a language will give you high-level features for you to write your code in an expressive way. But when this code gets compiled, it's going to be compiled to very low-level primitives. And the idea is that even if you're using these high-level abstractions, you don't get penalized in terms of performance or memory usage or stuff like that. And also, it's closely related to this generics monomorphization, which is simply code specialization. So for example, if you have a generic function that maybe takes an argument based on a certain interface, then at compile time, the compiler will look at all the types that implement this interface and generate appropriate codes for the type. So that when your code is running, you're kind of guaranteed that it will be code that is specific to the type of to the type at runtime. And this idea of having a zero-cost abstraction is actually not something new in Rust. This is something that has been borrowed from C++. So there's this zero overhead principle that C++ have. So if you don't use something, then you don't pay for it. And if you use it, you couldn't have written it any better. And this is sort of the mantra that Rust tries to also implement. So I'd mentioned about this slide. So this is simply showing the stages that Rust code goes through when it's being compiled. And it's important to know, like, these three first sections, they happen in the Rust compiler. So it has internally some intermediate representation. So this is the high-level intermediate representation, the mid-level. And then after that, it's going to produce this intermediate representation that's actually defined by the Llvm and pass it to Llvm. And then this part is now done in the Llvm backend. And this way, we are able to sort of get the optimizations for free that Llvm does. Yeah. Then the next thing in the Venn diagram was about safety. So there are several ways that Rust does this, but I think the most important thing is this thing called ownership. And the idea here is very simple. There are two things when you start looking at the memory issues that C and C++ have, is that you normally get these bugs when you have mutation and aliasing happening at the same time. With mutation, I mean you have a value in memory, and it's getting changed. And aliasing is when you have two or more references to the same memory address. And if you have these two things happening, mutation and aliasing, then bugs are bound to occur. So a good example is, imagine you have a variable that, and its value is a vector. So let's say a vector of size 2. And then you have another variable that's referencing inside this vector. So let's say to the first index. And then you mutate the vector. So let's say you double its size. And normally, based on the how these vectors are implemented, it might just be an array in memory. And when it goes beyond the allocated size, you have to allocate another memory block and copy things over to the new location. And so if you have these two references that don't know about each other, the second one that was pointing inside the vector, once the vector moves to another region of memory, will essentially be a dangling pointer. And the idea of the ownership system is to actually avoid such scenarios. And from the ownership system, you get concepts that are sort of built on top of this. So you have borrowing and lifetime. We look at them, but the idea here is to for you to actually do something, you need to share data or mutate data, and then you're going to have some sort of semantics and rules to use when you're doing that. And the last thing is going to be smart pointers that are kind of niche, but sometimes you have situations where you cannot actually describe ownership well. And these smart pointers are fitting in that, so they help you to describe some other cases, and I'm going to give an example. Okay, so the ownership method is simply a set of rules. So there are 3 rules. So one, each value has an owner, so a variable will own the value it has. There can only be one owner at a time, so you cannot have 2 mutable references to the same value. And if you want a value to be owned by someone else, you have to pass it to them. So you move ownership. And then the last one is when the owner goes out of scope, then the value is also reclaimed. So the idea here is a classic example. If you open a file in Rust, then the variable owns the file, and at the end of the scope, the file itself will be closed when the value gets dropped. Okay. So those are the 3 ownership rules. Then we have borrowing and lifetimes. So the idea here is very simple. For you to share data, you have some rules. One is if you're going to share data that's going to change, there's only going to be one mutable reference to this piece of data. And if you're going to share data that's not changing, so immutable reference, those ones you can have as many as you want. And the idea is that if one person is changing a certain memory, then you don't have risk of having dangling pointers or stuff like that. So here is some code just to try and illustrate how ownership and borrowing works in Rust. So this is a piece of code in Rust. So essentially, So you have a function that is formatting an integer into a string. And then here, instead of returning the value, we are returning a reference. So basically, a pointer to the memory location where the string is. But this won't compile. The reason being because since this is a reference to S, so S, if you think about S, S is the owner. And one of the constraints with referencing or borrowing is that this borrow cannot outlive its parent. So at this point, when we get out of the function, we are going out of scope. So this is going to be freed. And this essentially will be a dangling pointer. Yeah. And maybe I can try, see if we can actually see this. So sorry, but just a minute. All right, so this is the code in a Rust playground. So I'm going to run it and see what the compiler says. So yeah, so you can see that we get an error that says the borrowed value does not live long enough. And it will actually show you the scope in which S is valid, which is until line 14. Yeah. Okay. So essentially, that's what you get. Then, so here, this is an illustration where we have data that's mutable, that can change, and we also have an immutable reference to the data. So this is how you opt in to mutability in Rust. So we are saying here that this vector might change. Then here we do a reference to the first element, but this reference is immutable. And then at this point, we try to mutate the vector. And essentially, the compiler is going to complain and tell you you cannot have mutability and immutability at the same time. So essentially, you get this error that says you are doing borrowing mutably and also borrowing immutably, and we do not allow that. And it actually give you like a really nice error message showing you where you're doing it wrong. Yeah. And some people have actually thought that the compiler gives you great messages and say like it sort of does pair programming with you. Yeah. Okay. Then I mentioned about smart pointers. So this is an example. The idea is you have some memory that you want to share, but you're not sure of the ownership. So if you think of this, think of it like the TV in a family living room. So if you have a family, the first person into the room is going to turn on the TV, and they're going to watch, and people are going to come, and they're going to continue to watch. And then people might leave and go as they want, but the last person in the living room is the one who's going to turn the TV off. And there's no guarantee that this last person is going to be the first guy who turned the TV on. So you have some value that's being shared across several variables, but we don't have a clear owner. So the idea here is, actually this is just reference counting. So RC stands for reference counter. And we initialize our variable behind it. So here you have a reference to the reference counter. When we do this clone, this copy, we are just copying the reference. And here, we are essentially freeing the variable A. So at this point, we are going to just reduce the reference count. And even if this value has gone away, we still have this data because it's being allocated on the heap. And this will happily compile in Rust. So this is one of the ways to handle the issue where you don't have a clear ownership. And there's a counterpart, so there's there's RC, and there's also ARC, so ARC, which stands for atomic reference counting. And this is important when you're sharing data across threads and you want to ensure that you have thread safety.
So will this compile?
Yes, this will compile.
It's just a reference counter?
Yes, yes, yes. It essentially, the data here is on the heap, and what you get here is just a reference to the data. Yeah. And so the idea, if you want to think about ownership, the owner of the data is not A, but it's the reference count. Yeah. So, okay, so having made it so far in my talk, I'm going to reward you with a crop. So this is Ferris. It's the Rust unofficial mascot. All right. So moving on. So this is the last big idea in the three things that Rust tries to cover. So it's concurrency. And Rust supports concurrency in several ways. So you have various ways you can do concurrency in Rust. There's message passing, threads, the classic shared state, and a bit of async. So we're going to go through this. So with message passing, so the idea here is very simple. You have threads or actors that will communicate by sending messages to each other. So if you, and this is basically based on the actor model. If you're familiar with Erlang, Go, or I think it's Akka in Scala. So you kind of have this concurrency model. And the way it's implemented in Rust is you have essentially a communication channel. It has a transmitting side and a receiving side, so these two pairs here. And then, in this case, we're just spawning a child thread, giving it the transmitter side of this channel. It's going to do some work, and it's going to send back the result. And in the main thread, we just wait for this result and print this out. And so this is a nice way where you can do concurrency without actually having to share memory between the different threads. So this thing in the standard library is simply a multiple producer, single consumer channel. What it means is you can have multiple of the transmitters, but only one of the receivers. So you can spawn as many threads here you want and just clone this guy and pass it to them. And then you can get the results as they come. But also, there's a third-party library that actually implements where you can have multiple producers and multiple consumers. Okay. So the next thing is thread. So threading in Rust is pretty similar to C and C++. So you have OS threads. So it's a one-to-one mapping. There's no green threading or light threading in Rust. So here we are simply spawning a thread, and then we are passing in a closure. So the double pipe thing is to just pass in a closure to the thread, and the closure will contain the actual computation to be done on the thread. And then we just, here in the parent thread, we wait for the child thread to finish. Then there's the shared state. So here is where ideally, sharing state is not a good way of doing concurrency because you have the risk of having data corruption. But it's something that we actually use in writing programs, so Rust supports this. But what it does is that it forces you to have a locking discipline. So you cannot change data unless you have the lock. And to illustrate this, so remember I mentioned ARC, the thing for doing threads, safely sharing data across threads. And then you have a mutex, so which is simply gonna lock the variable. So in this case, you have, this is our initial value. The mutex owns it. And then this mutex, since it's gonna be shared across threads, we wrap it around an atomic reference count. And so here, we have a clone of the reference counting, so essentially incrementing the ref count. We create a new thread, and then we give it a closure here. So there's this keyword, essentially move semantics. So ideally, it means that this closure is going to capture its environment. So here, the counter is going to be moved into the thread. And we have to do this. For us to change the value, we have to actually lock. So, and this lock is where the mutex come. So for you to access the value, you need to first acquire this lock, and then we can mutate the value inside the mutex. And this way, it ensures that at any given time, there's only one thread that can actually have access to the shared data. Yeah. And then this is just similar to what we had seen earlier. Yeah. Okay. There's async in Rust is relatively new. It's not yet stabilized. There's a lot of work ongoing to get this stabilized. So recently, the community settled on the actual syntax for this feature, and it's now being implemented in the language. So this is actually one of the places if you're interested in Rust and you wanted to do a bit of asynchronous stuff. So at the moment, it's still in the works. It might not be actually something that you can be able to do in Rust, at least in stable Rust at the moment. Yeah. And so yeah, another crab for you. Okay, so we have covered more or less these 3 goals that Rust tries to solve. But then I had talked about Rust empowering us as developers. And I would want to give example of how Rust makes you good as a software engineer. So the first thing is metaprogramming, and this is kind of given if you work in higher level languages. Some of these languages have ways to express this. But it's important to note that Rust provides this macro that are hygienic macros. So it's something that's not new. Again, Rust likes borrowing from other languages. This is borrowed from Racket. And the idea is that you can write code like this. So, so here we have this struct. And by simply annotating these traits over here, so simply saying they should have this behavior, we are able to define a way to have serialization and deserialization into JSON. So essentially, you have this is a library that provides these 2 implementations, behaviors, and you can, as long as you have a struct, you can mark it as being serializable, deserializable, and from that you essentially get, a free way to do serialization either into JSON, XML, or whatever. And the key thing here is that the way this has been implemented is very generic. So it works for any sort of struct. And the idea is that if you have a behavior that is common to multiple things, then you can just write a debug macro and use it to generate code for all the specific types that you have. And essentially, this means you don't have to duplicate stuff. You don't have to write the same thing over and over again. It's the same. It's also similar to this macro here. So this is just hiding all the stuff that needs to be done. For example, getting std out to actually be able to display this on standard out, or if you're printing error or something. Then there's also really good support for generics, so using traits. So traits in Rust is simply a way for you to define behavior. So, and it's independent of a type. So like in this case, we are saying that any type that implements this behavior should have these methods. And you can actually also be able to even define what are called a default implementation. So when you mark your type to be implementing this, you can have a different implementation and you don't have to change it. And if you want to change it, you can sort of override it. And you can think this as being a way to actually do a bit of object orientation, where you have sort of a basic traits that defines the default, and then if you want to specialize it on a certain type, you can override it. So this is a trait. Then here, this is an idea of how you implement it. So you simply say we're implementing this trait for, this is a struct somewhere. and then you can just override one of the methods. The main thing is that you just maintain the signature. So like in this case, this is a code from a file downloader. So when we get the headers, we create a progress bar based on the content length. And then if you now have something that's doing the actual work and wants to say, I have this interface that I can take anything as long as it has this trait, then it's very easy to express that. So you have this structure here. I will break it down. So we simply have a vector of things that implement this behavior. And the ref cell here is to enable us to change them. So you have some mutability here. And then it essentially means that as long as there is a type that can have this behavior, we can accept it into this struct. And the idea here being that, so in this case, we want to give events when we are doing a download. And how we do that is you would have, so this is where we are using now our hooks, which was this vector. And then we just call the heads, and then we, on headers, and we pass in the data that we got from doing the head request. And this allows me to write data in generic ways, so I can have a new type, implement a trait, and it will still work for this. And just to illustrate this further, so this is a simple example. We have two vectors of cities in Oslo and the population of them. And we can do this using, so the Rust vector has a behavior of an iterator. So we get this for free, and we can do things like this. So make this an iterator, zip it with the population, and try to print out something. So who can guess what we get from this? So we have two vectors here. We make one the first one an iterator, and we combine it with the second one. And then we have this last thing, and we're gonna do essentially for city population in this metric, we're gonna print out the population. Yeah. So any idea of what you get when you do this? Yeah. No, so this is gonna compute, and essentially what do we get? What do we print out here? Mm-hmm. Someone else? Yeah, so population of Trondheim, because here we combine and then we just get the last thing. Yeah, and it's important because this is stuff that you get in Rust. And if you were to think about it, just imagine you're writing C or C++ and you have to do a similar thing. So again, you gain these high-level features for free, and you don't get penalized for them. Okay. So we also have some dev tooling that is really good in Rust. So I'm going to just touch on a few. So there is one called Rust Clippy. So the idea here is that it's going to catch like common mistakes and try to guide you to write better code. So you can, and it's very easy to integrate, with IDEs. I normally use Vim, and this works really well with Vim. And there are a lot of other IDEs that support Rust. And the idea here, like, you can get something that tells you you're passing this argument by reference. Maybe you should pass it by value. And this code will compile. It will not complain, but it's sort of like telling you this is a better, efficient way of doing things. you have a tool called RustFix. So, and the idea here is that it will help you migrate your code. So recently, there was the Rust 2018 edition. So Rust, there was a stable release in 2015, and they made a breaking change in 2018. So you have a newer edition of Rust that is not really compatible with the old one. And part of the thing they did is they provided tooling that you can just use to actually migrate your code over to the new edition. So an example here is this is an anonymous field that was valid in the previous edition. And then we can just call this command. So cargo is the Rust build tool, and it will automatically update your code to look like this. And this will work in the current edition. And so this is kind of nice if you have a really huge code base and you want to do refactoring, and you don't want to manually go and find all the various places that you need to change. So you have tooling to help you with that. And the last one is we have a Rust format, which is essentially, again, this is not new. We copied it from Go. So there's Go format. Now we have Rust format to help you format your code, make it easier to do CI and stuff like that. And so that is just a diff showing some code formatting. Okay. So I really like this quote. It's about what software engineering is. And it's a quote by Russ Koch. He's one of the main Go developers. And the idea was that programming is what happens when time creeps in and more people start contributing to your project. And he talked about several things to paint this picture. So if you think about it, if you have virtual control software, so like Git, it enables you to go back in time. So today, we made a change. It broke production. We can revert to yesterday, and everything is OK. You have CIs, so continuous integration, ensuring that any feature that you add in to your system does not break the system. You have unit testing that makes sure that a feature, when it's implemented, is not going to be broken sometime in the future, right? You have refactoring. So what I was just talking about, you have an old way of doing things. You have a new way. So you're essentially moving from the past to the present or to the future. You have design patterns. So and the idea of design pattern is that you want it to be easier for the future you to like change things or like adapt things or grow or scale the code base. And I think these are important ideas, and I wanted to just showcase how Rust makes it a bit easier for you to do. I already talked about refactoring. We have essentially, if you want to write a test in Rust, it is as simple as just annotating a function being a test, and it will the build tool will run this as a test. So this is someone talking about refactoring. I'm not nitpicking here, but so he says it made it easier for him to do multi-threading in a way that he couldn't have done using C and C++. Then I talked about having being able to refactor your code. So this is the Rust 2015, and you have Rust 2018, and we are able to migrate your code to the new edition. And also something cool that Rust does is, for example, if I'm writing Rust now, I'm writing in the newest edition, but I can have a dependency that was written, I don't know, 4 or 5 years ago. It's stable, it doesn't change. So it means it's essentially in this old edition. And Rust will actually compile my code. So it will use the old edition to compile this library that I rely on, and use the new edition to compile my code. And so it guarantees that even as Rust grows, if you have dependencies that you don't control them, then they will not break because the language changed. And if you do Python like me, you understand that sometimes you have this where your dependencies are all over the place. And it's really nice to have a tool that tries to solve this in Rust. And essentially, they use Semver, so you have semantic versioning to make sure that things don't break. And if they break, you've actually done it using the semantic version by changing a major, moving up to a major version. Yeah. Then we also have a community repository. So essentially, if you have a library and you want to share, you can simply upload it to Crates.io, and then everyone has it. And also, it's a nice way for people to discover what has been built. It can show you, how a crate has been downloaded, who is using it, and that way, if you're looking for something, it's easy to know if it's people are using it, what is the state, and also you have only one place you can come and find whatever you want in the Rust ecosystem. So yeah, so another crowd for you. So I realize I'm a bit out of time, but I'll try cover a bit more, so you forgive me for moving a bit fast. But if you're interested in using Rust for trying out a project or integrating it with what you have, there is a list of companies that actually are using Rust in production. So, and you have people building storage engines, databases, web servers, and stuff like this. There's a lot of things being done. And this is a place where you can go and actually see the companies that are using Rust and what they are actually using it for. Yeah. So I work for Snips, and what we do is essentially have Rust for embedded development, and it has worked really great for us. I'd mentioned about the last thing I wanted to talk about was community. So Rust is kind of all over the place. This is a map of people who have talked about Rust on Twitter. There are a lot of, if you look around, you're going to find probably a meetup that's close to you. And I found it's easier if you're trying to get into Rust to actually join a meetup group. People are friendly and they can help you, and you also have a sense of community. And there are also conferences coming up. People are doing conferences, I think, here in Europe, in the States, and also in Asia. Yeah. And then, so lastly, if you don't know where to start, that is the homepage of Rust. It has a lot of the documentation, how to start learning, and also the people who are using Rust and all that good stuff. So, and yeah, thank you.